Hello everyone. So today we are going to look at the theory of superposition, and by the end of the session hopefully you should be able to solve some simple circuits with multiple independent sources using this theory. So what exactly is superposition? Superposition is a property of linear systems, and this is the category into which simple electrical circuits like the ones we have been doing with RLs and Cs fall into. And there are others, of course, like the power system and things where you have semiconductors and diodes and so on, the kind of things you'll be doing in electronics. Some of those do not fall into the category of linear circuits. Now the interesting thing about linear circuits is it allows us to deal with a system containing multiple sources, one source at a time. And in case you forgot what linearity is, it is essentially if you scale up the input, the output scales by the same amount. So the way we go about doing superposition is very simple. What we do is you start with one source that you want to look at and you turn off the other sources. This means that you short circuit the voltage sources, because if a voltage source is turned off, the voltage across it is zero. And for current sources you open circuit them, because if you turn off a current source, then it means the current through it is zero, which is an open circuit. And then you determine all the voltages and currents in the system which now only has one source. You do that for each source independently, and then you add up all your results and you will get the result for the total system. So that is basically what superposition is. So we'll just go through 2 or 3 examples and you'll see how it works. So the first example, we have this 2 source circuit, 10 volts, 12 volts, and we have 3 5-ohm resistors, and we want to basically find these currents I1, I2, I3. So the first thing we're going to do is we're going to consider the 10 volt source. That means we have to turn off the other sources, in this case the 12 volt voltage source. So turning off, that means we are going to short circuit it. Right, remember this is a voltage source, so turning it off means the voltage across it should be zero. So we turn it off, which now becomes this short circuit. And you'll see this is part A, so I just labeled the subscripts here 2I, 2A, I1A, I2A, and I3A. Good. So now we're going to find these currents I1A, I2A, and I3A. We know that the current I1A will be the voltage 10 volts, which is here, divided by the total resistance. And the total resistance, if we simplify this circuit, this will reduce to 10, and this here is 5 in parallel with 5, which is 2.5 ohms. So the current from the source is 10 over this should be 5. 10 volts over 5 plus 2.5, which gives us 1.33 amps. So we have 1.33 amps flowing this way, and it splits between 2 5-ohm resistors. We could use our current divider, but since the resistors are of equal magnitude, it will essentially work out to be a half. So 1.33 divided by 2, and we get 0.667 amps for I2A and I3A. So we've worked it out for the first circuit. For the second circuit now, this is our original circuit here at the top, the original. And for the second circuit, circuit B, we are considering the 12 volt source. And when we consider the 12 volt source, now we have to short circuit the 10 volt. And we essentially do the same thing again. Now, this time I have labeled my arrows here going in the opposite direction. Notice what are the directions of the arrows here. they're in the opposite direction here. Really, I could take it in any direction. It doesn't matter once I resolve the directions at the end. So here now I just did it so the 12 volts will be positive. Otherwise, if I put them in the other direction, I would have to say 0 volts minus 12 volts. So anyway, again, we could simplify this circuit, and this would give us a circuit like this: 5, 2.5, and 12 volts. So I have 12 over 5 plus 2.5, which is 1.6 amps, which is this current here, 1.6 amps. And then that splits equally between these two since the resistances are equal, so I get 0.8 amps each. So these are the two sources, and I did them one by one, and now I have to combine the results. So I have my original circuit here at the top, then I have circuit A, and I have circuit B. So notice the direction of I1 here. I1 is going in this direction. I1A is also in this direction, but I1B is in the other direction. These currents are all set by me, so I could have set them in any way I want. So now from this I could see that I1 is equal to I1A, which is in the same direction, minus I1B, since I1B is going in the opposite direction. And if I look at that, I would get, if I combine the results from the previous slides, if I go back here, you'll see I1A is 1.33 and I1B is 0.8. So this is 1.33 minus 0.8, which will give me 0.533. And I do the same thing for I2A and I2B. So I2 is down, I2A is down, and I2B is down. So that means I2 is equal to I2A in this case plus I2B, and that gives me 1.4667 amps. And the last one, I3, you'll see I3 is in this direction, I3A in the same direction, I3B was in the other direction, so it's I3A minus I3B, and that gives us 0.933 amps. So now you could pause the video here and try this question. And remember, this one we have a current source, so we deal with it a little bit differently. So go back and you could look at how we deal at the current source, pause the video and try to work it out. Good. So by now you should hopefully have something if you pause the video. So we're going through the same process here. The first thing I do is I have two sources, so I'm going to redraw my circuits with only one source at a time. So I'm going to create now circuit A. And circuit A is going to consider the 10 volt source. So I have my 10 volt source and 5 ohms, 5 ohms, 5 ohms, and now I have to turn off the current source, which means the current has to be 0, which is an open circuit. And I designate my currents I1A, I2A, I3A. So from here I could see that I3A, since it is open circuit, is 0. And all the current flows through essentially I1A and I2A. So we have this part of the circuit here being out, and the current simply flows like that. So I1A is equal to I2A is equal to 10 volts over the total resistance, which is 10 ohms, which is 1 amp. So now I have my my first set of results. I1A and I2A 1 amp, I3A is 0 amps. Now I'm going to do it for the current source. So looking back at my original circuit, now I have to turn off the voltage source. So I'm going to look at circuit B, which is the current source, and I have to now turn off the voltage source, which means I'm going to short circuit it. And now I have my current source, 2 amps, 5, 5, 5, and now I'm going to designate the currents again in the opposite directions. And I didn't have to designate them in the opposite directions. Well, let's, for fun, just designate them in other directions. So I'll designate in random directions. So this will be I1. I'll put I2. This is I1B, I2B, and I3B. We put in that direction. So now I could see that I3B is equal to minus 2 amps because it is going in the opposite direction from the 2 amp. And now I have I1B and I2B. Now the current in reality is going to split equally between these two 5 ohm resistors. So we'll have 2.5 amps going this way. I1B is equal to, sorry, we'll have 1 amp going this way since it's half of 2 amps over 2. If we want to do it with the whole current divider equation, 2 into 5 over 5 plus 5, which is 1 amp. And similarly, I2B is negative 2 over equal to negative 1 amp. And this is negative, of course, because in reality the current will go down, but we have designated I2B to be up. So now I have my second set of results. So now I could compare the results and see what I have. So let's do that now. So this is my original circuit. The first circuit, circuit A, was this. I1A, I2A, I3A, and then the second circuit and here we have I3B. Oh, we have I3B in the opposite direction. I3B, I2B, I1B. So I could say here by comparing the directions that I1 is equal to I1A minus I1B, and I1A, if I remember correctly, was 1, and I1B was 1. So that is 0. Then we have I2, which is equal to I2A minus I2B, and I2A was also 1, and I2B was minus 1. 1 minus minus 1, which is 2 amps. And then we have I3, which is equal to I3A plus I3B, since it's also in the same direction, and I3A was 0 and I3B was minus 2. So we have minus 2 amps there. Good. And then we have I1, I2, and I3. So from this we could see that we have no current flowing in I1, and we have the 2 amps here, which is I3. So we see it is in the opposite direction, so it's minus 2 amps, and we have 2 amps from I2 going down here, which gives us 10 volts across the resistor. And since we have 10 volts here and 10 volts here, then we have no current flow through this resistor. So it is all quite consistent. Right. So the next thing we will look at is superposition with dependent sources. So we did an example with only independent sources so far, current sources and voltage sources. Now we're going to look at what would happen if we have dependent sources. And now dependent sources should be treated really just like passive components, right? So we don't turn them off at all. We still only turn off the independent sources. So for example, suppose we have a question like this, and we need to find the voltage across R4. And we have these two sources, the 10 volt source and the 20 volt source. Here we have our source or dependent sources of dependent voltage source, and its value is 3 times Vx, and Vx is the voltage at this node here. So again, the first thing we're going to do is we're going to do one source at a time. So we're going to look at our 10 volt source. So when we look at the 10 volt source, now we're going to short circuit the 20 volt source, and this is the circuit we're going to get. So now we know here will be 0 volts, and we want to find what is the voltage at this point here. We know here is 10 volts, and this point here, which is VR4A, will be equal to 10 volts plus the voltage across the voltage source, which is 3 Vx. Now we need to find what is Vx. So here we have a circuit where we have 10 volts, and we have 5 in parallel with 5 and in series with 10. So if we look at this part of the circuit, it's 10, and then we have 5 in parallel with 5, and this voltage here is Vx. So this is 10, and we have 5 and 5, which reduces to 2.5 ohms if we use our parallel resistors, our equation to find equivalent parallel resistance. So what is the voltage here now? If this is 10 volts, Vx is equal to, using our voltage divider equation, it would be 2.5 over 10 plus 2.5 multiplied by 10. So we have 2.5 over 12.5, which is 0.2 volt multiplied by 10, which is 2 volts. So Vx is 2 volts. So 3 Vx, now we could say VR4 is equal to 10 plus 3 by 2. VR4A is 16 volts, and that is the first part. Now we do the second part. So we short circuit the 10 volt and leave the 20 volt in, and again we want to find, this time we'll get the voltage this way. So we have, and this will be VR4B. So we know this side is 20 volts. We know this is 0 volts. 0 volts. And this is now 0 plus 3 Vx. So we have 0 plus 3 Vx volts, and Vx here is, right, good. So we have 3 Vx volts here, and we have 20 volts on this side, and the difference between them is VR4B is, look at the direction the arrow is pointing, so it is 3 Vx minus 20 volts. So again we have to find Vx. So what is Vx? If we look again at this part of the circuit, we'll see, which is in parallel, so we could analyze it separately. We'll see that we have 20 volts and we have a 5 ohm resistor here, and then it splits to a 10 and a 5. And Vx is essentially the voltage across here. So we have 5, 10, 5. We could further reduce this to 5, and this is 10 in parallel with 5, which is 50 over 15 ohms. So we have now Vx is equal to, okay, so now we need to use the voltage divider, and that would be 50 over 15 plus 5 multiplied by the voltage, which is 20 volts, and that should give us 0.4 by 20, which is 8 volts. So Vx is 8 volts. Therefore VR4B is 24 minus 20, which is equal to 4 volts. So now we have to find VR4. So we took VR4 in this direction, going left. So we say VR4 is equal to, now we have to get the directions and the values of VR4A and B. VR4A, which is 16 volts. So we see 10 plus 3 by 2, which is 16 volts, which is this direction. 16 plus, and now we need the 20 volt source value, so VR4B, which is 4 volts, also the same direction, and we see that the voltage across that is 20 volts. So let's just verify that all the directions are the same. This is the direction we want it in, going left. What is the direction we took for the 10 volts? That direction. Direction for the 20 volts, same direction, and we end up with adding the two and we get 20 volts. So hopefully by now you should be able to solve circuits, some simple circuits with multiple sources, even if they are combinations of current sources and voltage sources, and with dependent sources as well. Next time we look at doing the same thing but using loop analysis.